Hi, we are moving on to standing wave. Before you start this video, make sure you go through the two demonstrations which are included on the playlist. The best way of learning standing wave is to draw the diagram and try to count how many wavelengths are there. And so in this video, this is something that we are going to do together. Okay, so I'll demonstrate you some of the examples and you'll be able to draw the rest by yourself. So the first one that I would like to focus on is the diagrams of two fixed ends, just like the slinky in the previous playlist video. And so think about this, the first possible standing wave that you can get, which we also call as fundamental frequency, is something like this. This diagram you can interpret it as this is the two end, and then here we've got a node, and well, maybe I can draw here we've got a node, here we've got another node, and then here we will have an anti-node, right, which is having the greatest amplitude. So in case you don't know how to interpret this, this is how the particles along the string will be moving. And so in this case, imagine you're now changing the frequency and maintaining the string as the length as L. Think about this. How many wavelengths are there within this 1L? The answer is half, because think about these, and then you can continue to draw this, okay, and then this whole thing will become one cycle, okay, one wave. So therefore, the one that you are having within the string is only half of the standing wave wavelength. So I'll put L equal to lambda over 2. So this is the first case that we have. Now let's try to do the second harmonic, which again will maintain the distance of the string, but then now imagine you are increasing the frequency. So what could possibly be the pattern then? The next possible pattern should be something like this. Okay, so you can follow me and draw it on your own booklet, and then obviously, if you want to, you can annotate like what I do here. This is a node, this is another node, this is also a node. Of course, the two fixed ends must be a node, but then now you have one node in between them. And for the anti-node, you have it here and also here. So now it kind of go to the next level of this standing wave, which again we call it second harmonic. So once again, I would like you to figure out how many wavelengths are there. And for this one, it's just very obvious. It's going to be 1 lambda simply. So for now, I would like to give the time to you. I will want you to do the same thing for the third and fourth harmonic. Remember, you are going to maintain the length to be the same and try to figure out how would the pattern look like for the third and fourth harmonic. So pause the video now and try it out.
A few moments later.
Okay, let me demonstrate to you. From the pattern you could see actually the second harmonic you have one new note there, and so for the next one obviously you are going to get 2, and I guess they should split the space equally. And so this is the way you can try to rely on, and we get to here, and then we get to here, and then we get to here. Okay, and then I will also draw the envelope of the standing wave like this. So I'm not going to annotate the rest, but I think you will know which one is the node, which one is the anti-node position. So for this one, we have to determine the length, and that is, here is 1 and this is another half, and therefore you have 3 lambda over 2, or 1.5 lambda if you like to say. And so for the fourth one, is become more obvious to you now, and that is the reason why I designed this to you. I want you to experience how to draw them, and once you know how to draw it, it's very easy. So node to another node to another node and to the end. Okay, and then we would also again draw the envelope. Okay, nice. And then now this length will equal to 2 lambda simply. Before we move on to the second case, one more thing that I'll need to do is I want to figure out the expression of each of these frequency. So how we are going to do it is to rely on the expression we put down between L and lambda, and let's just recall for wave equation that is V equals to F lambda, and therefore lambda would equals to what? V over F, right? And so in this case, then we can rearrange it. So then this would become V over F2. And so in this case, we can get the frequency we call F1, because this is the fundamental frequency or the first harmonic, would equal to V over 2L. Similarly, for the second harmonic down here, then we can do the same thing. So it's going to be V over F2 times 1 if you like to write. Then this, maybe I can write here. Then this will imply F2, second harmonic frequency, equals to V times, L times V. Same for the third one. It's going to be V over F3, and then the coefficient 3 over 2. And therefore F3, third harmonic frequency, will equal to V over L 3 over 2. And I guess you can tell from the pattern that this is going to be V over L times 2 simply. And so you may say, hey, so what are we trying to do then after we calculate all these things and finding out all these expressions? Are we expected to memorize all this? Of course, the answer is no. We can deduce further and try to find out the pattern. And this is what physicists will do, find out the pattern. So for the first harmonic, let's take a look. It has a coefficient, if you look at the expression, of 1 over 2. And for second harmonic, it is going to be 1. So it's like a double. And then for the third harmonic, it's going to be 3 over 2. So if you try to think about the pattern, and also the last one is going to be 2. And in fact, for 2, you can rewrite it as V over L 4 over 2. For 1, it's actually V over L? Wait, I just find out I make a mistake. V over L, sorry. Alright, and then it should be equal to V over L 2 over 2. Right? It may look stupid, but then if you now try to look at all the coefficient, you find out they are all correspond to the first harmonic. And so that is to say, if this is the fundamental frequency, F2 is going to equal to 2 times F1, right? If you look at the coefficient. And F3 is going to be equal to 3 times F1. And similarly, F4 is going to be equal to 4 times F1. And that's why we call first harmonic, second harmonic, third harmonic, and fourth harmonic. And in this case, you can now generalize that for the nth harmonic, then it should equal to n times frequency 1, the first harmonic. Now let's move on to the second case. Things should get more systematic now. This diagram is going to be two open end. So like the musical instrument that earlier we talked about, the two ends are open to the air, and therefore they are kind of loose end. The amplitude will be maximum, and that is the n-type note. So how I will draw it is I will be drawing a pipe like this, and if the two end is going to be n-type note, then you can imagine it's probably something like this in this case. No, sorry, this is not because the wave can't be vibrating like this, so it's not curving this way, it should be curving like this way. Okay, so when you draw it, you want to be more careful with how you draw the curve as well. So the envelope will be something like this, so it will be vibrating like the envelope is like this. In fact, the movement of the air is not like this in this diagram. It's actually going horizontally, right? Because this is the compression and rarefaction that we have along the whole pipe. And this is just to illustrate the standing wave inside only. To show you a better idea, here we've got a simulation which I'll put down the link in the description below so you can try it yourself also. Let me show you the case number 1 first. So the string, the 2 fixed end that case. So this is the first harmonic, this is the second harmonic, so exactly the same like how we drill. This is the third harmonic. Now we go to the open end air column, which is the 2 open end like the one that we did just now. So this is the first harmonic that we can draw. You cannot draw anything simpler than this. You can think about it, you try to think about it. Again, this is not really how the air moves, right? The pipe, I mean, think about it. If you blow the air in, the air doesn't go like vertically in this diagram. Like it should go along where you blow the air. So how it actually happened is more like the longitudinal wave here. So you can try to observe the animation and understand the movement. Okay, so similar to what we did, now what we have to do is to figure out if this is again the length L, how many wavelengths are there? The answer can be checked by extending the length further. So think about this. If you can extend it further, here will be another quarter, here will be another quarter to start over again at the same spot. Okay, so obviously the one that you have within L is going to be half of the wavelength again. So now maybe I'll also demonstrate the second one and you can follow me. So once again, this 2n is always anti-node because they are open end, so it must be being the anti-node. And then earlier here we have got a node here. So just using logical thinking, that if there was one node here, then probably in the second harmonic, then we should have 2 down here. And so we could have something like this. Oops. And in fact, you should find there should be one node in the middle. So I guess I should split this into equally 4 partition instead of now it's more like a quarter for each. So the scaling I could have done it better. But anyway, this is just to help you and guide you to think. So for now, same question. L equals to how many? And so this one is obvious. This is going to be 1 lambda, and I guess you may guess how it will happen at the end after you draw the other 2. And this one I will express it as 2 over 2 lambda. And just doing the same thing like what we did earlier, then you should find the first frequency, the fundamental frequency or first harmonic is going to be the same thing, V over L times 1 over 2, and this one is going to be F2 equals to V over L 2 over 2, and that is also 1 of the fundamental frequency. Anyway, I'll still want you to draw the other 2, so the third and fourth harmonic. Pause the video now and try it yourself.
A few moments later.
Okay, so this should be the third one which I prepare. There are 2 anti-node in the middle because the second one you have 1, for the fundamental frequency you have none, and therefore for the third one you should have 2. And so the wave should look like this. Okay, draw better. Okay, and then the envelope. So once again, you should find L equals to 1.5. So 3 over 2 lambda, because I think you can see clearly this is 1 and this is another half. And so again, you'll be able to deduce, similar to case 1 where we have 2 fixed n, F3 is going to equal to V over L, 3 over 2 equals to 3 times of the fundamental frequency. And now I'm going to do the fourth one. Right, which are very tightly packed together. Okay, but anyway, this is how the drawing should look like if we maintain the L. And so that's going to be 4 over 2 lambda, or just simply 2 lambda. And again, what you can deduce is F4, fourth harmonic frequency is going to be V over L, 4 over 2, which equal to 4 times of the first frequency. And so once again, that is to say, for the 2 open-ended case, the frequency of the nth harmonic is going to be equal to n times of the first harmonic. Now let's get to the last case, because think about this. You can either be open-end or closed-end, right? And along a tube or along a string, you can either have 2 fixed, 2 opened, and the last case is 1 open, 1 fixed, or you can say closed or open. And that's all. I mean, thinking about like all the possibilities, these 3 are all the possible cases. So now we are on the last one. So the first harmonic we can do is by drawing the pipe first. So like the demonstration video I showed you, some instrument will have one side to be closed, one side to be open, and therefore they will produce a different sound even they are of the same length. And so for this one, obviously for the fixed end, this is going to be this is going to be node, and this side is going to be the anti-node, and therefore the wave will look more like this. Alright, I should draw a dotted line. Okay, so this is the amplitude. Okay, you can also double check that with the simulation. This is how it looks like, although they kind of flip the other side is okay. You can also check the longitudinal wave as well. Yeah, so this is how it looked like. So now, similar to the previous cases, let's do it systematically. If this is going to be L, how many wavelengths are there? If you think it is half, then you are wrong, alright? Because this one is very tricky. For the other two, you can see it's always half of the wavelength for open end and also half of the wavelength for the 2 fixed end for the first fundamental frequency, right? They are all the same. But for this one, it's a bit special. If you try to extend the wave that you drill to this is going to be 1L. And then this is not the whole wavelength. This is only half in total. And therefore you have to draw this, and then this, and eventually this is one whole cycle of the wave. And therefore the wavelength that you have within 1L is only a quarter. Now I want you to try drawing out the second harmonic for this case. So pause the video and try yourself.
A few moments later.
Okay, so let me demonstrate to you. You should have one note here. And then here you can only, because this is also note. So at the end, oh wait, not this side. At the end, you have to reach back to this point and keeping it as the note. So this is the only choice that you can make. And yes, there will be an anti-node here. So once again, if you, based on this picture, if you try to find out L equals to how many wavelengths, how many would it be? The answer is going to be 3/4 of the wavelength, right? Because this is not one completed, only 3/4. Now, please try to do the third and the fourth harmonic. Give yourself some time, pause the video, and try to draw it yourself.
A few moments later.
Okay, the third harmonic, we would have note here, go down to the note, go up, and then to the note. So this will be the envelope. For the expression, is going to be L equals to, this is going to be 1.25, so it's actually 5/4. For the fourth one, then yeah, it's the same work. So we have 2 nodes here, then now we should have 3 nodes inside, and then we can draw the envelope. Down here, down here, down here. Okay, and then the expression L equals to, guess what? I mean, if you look at the number, you can also guess it should be 7/4 lambda, because this is 1/4, 3/4, 5/4, and this is 7/4, and you can deduce the rest obviously. And you can double check with the diagram. From here, okay, I'll draw here, from here to here, this is 1, and then the rest will be 3/4. So in total will be 7/4 lambda. So obviously for this one closed, one open end situation, it's different from the 2 cases earlier, and therefore it should yield a different result compared to the previous 2. And so let's just try to do it carefully and deduce the result. So starting from the fundamental, V equals to F lambda for the wave equation in general, then lambda equals to V/F, then we can have L for the first case equals to V/F 1/4, and therefore first frequency F1 will equal to V/L 1/4, and in fact the rest will be similar. You should get F, I mean if you look at this 1/4, it's going to be the same as this 1/4, then the rest will be easy. So F2 is going to be 3/4 V/L, same here, F3 5/4 V/L, F4 to be 7/4 V/L. And again, you want to compare how the other harmonics to the first harmonic. And so if this is going to be F1, then F2 is going to be 3 times of F1, F3 is going to be 5 times of the F1, and F4 is going to be 7 times of the F1. And so strangely, you only find for, again, case 3, there are only odd number, because this is 3, 5, 7, and obviously the next one is going to be 9 times F1. And so in fact, I have been lying to you and simplifying the case for you. For case 3, that means one closed, one open end situation, there's only odd number for the harmonic frequency. So we'll call the first one as usual fundamental frequency or first harmonic. The so-called F2 here, we actually don't call it second harmonic, we call it third harmonic, because it's literally 3 times of the first one. Okay, and that means F3, this one, this F3 is not called as third harmonic, it's actually the 5th harmonic. Similarly, for F4 here, it's actually the 7th harmonic, because it's 7 times of the first one. Alright, so let's try to draw the conclusion now. For the first 2 cases, which means 2 opened or 2 closed end, right? Case 1 and case 2, they are all the same, so I'll group them together. While for the case 3, 1 opened, 1 closed will be different, and therefore we'll put it into another row. So for the two open, two closed, that two cases, the frequency for the nth harmonic is going to be n times of f1. While for one open, one closed, that one, as we said, is going to be odd number only. So f2, for example, is going to be actually 3 times of f1. f3 is going to be 5 times of f1, and therefore you can conclude that fn, if you just count how many cases by n case, then we can say it's actually n times 2, shall we say? Not really. N minus 1 times 2 plus 1. Okay, but then I think that is going to get so complicated and it's not really necessary for studying physics. I think as long as you know, then that's okay. Or it also depends on how you define f2 and f3. In fact, if we stick with the fundamental idea of how we call them the harmonics, then it's okay. We can actually call this as f3 and this as f5. So that means here we will just simply change the definition itself into f3, f5, and f7 if you want to. But I guess here the most important thing that you should recall is there are only odd harmonic. And so in this case, we can then change this into f3, this into f5, this into f7. Then our definition would simply be easier, that we can still stick with fn equal to n times f1, however only for odd harmonics, and that means only for odd number of n, and such as 1, 3, 5, 7 onwards. I also want to express the general term for the wavelength as well. So if you try to look at this, the first case, we have lambda equal to 2L, right? If you just move 2 to the other side. And the second harmonic is lambda equal to 2 over 2L. And then this one, lambda equal to 2 over 3L. So if you try to look at these pattern, then you will find out the pattern is for lambda n, it will equal to 2 over n L. You can try to double check with your own answer with this general expression. And so for case 3, that means one open, one closed, that situation, lambda will equal to 4L for the first case. Next case is lambda equal to 4L over 3, and the next is 4L over 5, and I guess you can now see the pattern. It will be lambda n equal to 4 over n L, again for odd number of n only, which is 1, 3, 5, 7 onwards. And that's about it, guys. In fact, you may find this table is somewhat hard to interpret, and later on when you try to do some practice, you'll find out you don't actually have to record this directly if you can draw the diagram. So that's why in this video I emphasize a lot on how you can imagine the diagram, draw it out, and then count how many wavelengths are there. As long as you can do this properly, correctly, then you can deduce the frequency or the wavelength by yourself. And that is all for this video. In the next video, I'll try to do more practice question with you. Please hit the like button and subscribe to my channel. I'll see you again in the next video. Bye.